Thank you for joining Myron Zucker University in the Power Factor 101 training module, Power Factor Introduction. In this module, we will discuss the following topics. What is power factor? Causes of power factor, and more importantly, causes of poor power factor. How to improve power factor, and the benefits of power factor correction. This training is intended to be an introductory discussion with theory and mathematical calculations purposely omitted. These will be studied in greater detail in subsequent training modules. What is power factor? Power factor is a measure of how effectively a facility uses electrical energy or power. Since electrical power is provided as volt amperes, or more commonly kilovolt amperes, kVA, power factor is defined as the portion of delivered kVA that is actually used to do the work. Power factor is not to be confused with efficiency. Power factor can be quantified or measured using many methods and expressions. These are kVAR, kVAR hours, kVA, kVA hours, the ratio of kW to kVA, the cosine of the phase angle difference between voltage and current, the cosine of the angle whose tangent is kVAR hours divided by kW hours. The point here is that there are many expressions for measuring power factor, and they are all related. We believe at this point in our training it is important to boil down the definition of power factor to just a few words. The definition of power factor can be reduced to unnecessary line current. And since infrastructure such as generators, transformers, switchgear, and conductors are sized based on current, poor power factor results in the need for larger, more costly infrastructure. Also note that the expressions mentioned earlier for power factor can be reduced down to a single value, which is presented on the utility bill either as a decimal or percentage. Again, these relationships and theories supporting them will be covered in future training modules. It seems reasonable that if utility providers are required to install additional unnecessary infrastructure, costs associated to this will be passed on to those energy users operating with low power factor. This charge is typically based on a threshold value, and power factor values below this are usually referred to as poor power factor. The threshold value and method of calculating the power factor charge varies from utility provider to utility provider, and the power factor charge is commonly listed on the utility bill as a power factor penalty or power factor adjustment. It can also be listed as excess kVAR or kVA. So what causes poor power factor? Inductive loads cause low power factor because inductive loads require reactive current. Inductive loads include electric motors, induction furnaces, transformers, metallic ballast fluorescent lights, and compact fluorescent lights. Since 65% of the total U.S. industrial electrical consumption results from motor load, electric motors are the primary contributor to low power factor. A typical industrial electric motor at full load operates with a power factor of approximately 86%. The power factor resulting from electric motors is reduced even more if the motor is lightly loaded due to an oversized application or operated intermittently. Intermittent motor applications could include HVAC systems, molding equipment, presses, machining, grinding, and sawmills. Improving power factor. How can power factor be improved or corrected? The power factor of inductive loads can be improved by employing capacitors. Capacitors are passive electrical components, and when part of an AC circuit, provide reactive currents. As previously mentioned, inductive loads require reactive current. With capacitors in place, these reactive currents are no longer supplied by the utility provider because they are now supplied by the power factor correction capacitor. Therefore, reducing reactive current required from the utility provider improves power factor. Power factor correction capacitors can be installed at the load or at the service entrance. At load installations provide reactive current for individual loads, and service entrance installations provide reactive current for the entire facility. Service entrance power factor correction capacitors can either be fixed or automatic. Fixed systems provide a constant amount of correction for facilities operating with constant loads. Automatic systems adjust the amount of correction for facilities where loads are variable. Since we now know power factor correction capacitors reduce the reactive current required from utility providers, How does this translate to decreased line current? Reactive current is a component of line current. Therefore, a reduction in reactive current results in decreased line current. It is very important to understand that though line current is reduced due to power factor correction, real power kW, or real energy consumption kW hours, are not reduced by any significant amount. Why correct for power factor? It has been shown that a reduction in line current is a result of power factor correction, but what benefits does this provide? There are 4 primary reasons to correct power factor. These are 1. To reduce utility bills, which was touched upon earlier. 2. Free up system capacity. 3. Reduce distribution losses. And 4. Improve voltage. One must note that statements such as improve the efficiency of electrical devices and reduce electrical consumption by 20 to 30% are not benefits of power factor correction, as claimed by some in the business of selling power factor correction capacitors. Let's take a closer look at these benefits. Benefit 1 is to reduce utility bills. This is the number one reason for power factor correction. This eliminates or reduces the power factor charge component of the utility bill. Depending on the utility provider and the power factor value, the power factor charge can be as high as 30% of the utility bill. This example bill lists the power factor for the billing period as 0.770, power factor penalty factor of 2%, and the penalty charge of $1,442. Benefit 2 is to free up system capacity. This can include freeing up additional capacity in transformers, switchgear, and conductors. Reductions in line current and the resultant capacity increase within a facility are approximately 15 to 20% for a typical power factor correction project. Note that the additional capacity is only realized in the equipment located upstream of the capacitor point of installation. Benefit 3, reduced distribution losses. Distribution loss reduction does translate to a decrease in kW and the resultant real energy savings, but these are typically only about 1%. Since distribution losses are a function of current, distribution loss reduction is only associated with equipment or conductors located upstream of the point of capacitor location. Benefit 4, improved voltage. Capacitors connected to a circuit will cause the nominal voltage to rise during steady state mode. This is typically around 2%. To recap this training module, poor power factor results in unnecessary line current requiring additional unnecessary infrastructure. Power factor correction capacitors provide reactive current, thus reducing line current and improving power factor. Reducing utility bills is the number one reason for improving power factor. Improving power factor does not reduce energy consumption significantly. Please continue to the next training module, Power Factor 102, where example calculations will be used to estimate power factor benefits. Thank you for joining us in Power Factor 101, and have a great Power Factor day.